I can't stress enough how easy it is to use Ampere's law. And so to illuminate you, Ampere's law, this is not really Ampere's law. It is a modified version of Ampere's law. But I'm putting it here because we have to start with the modified version, and we will eventually get to the full version of Ampere's law, because Ampere's law has additions that have to be made to it. Believe it or not, Gauss's law is the same way, but there's no point in telling you that first semester, that we've only looked at a modified version of Gauss's law. So this modified version is a simplification of Ampere's law. But I'm supposed to put a little ENC here, but it's too small to write. It's IENC, I enclosed. So Gauss's law, if you remember, was the charge enclosed was proportional to the total flux through an area. Ampere's law is the same thing. It is the current enclosed is equal to the total magnetic field, but it's not a flux. I haven't even said anything yet.
I was just curious, is it DS?
Uh-huh. Okay. Oh, you can't read my handwriting?
I just didn't see the S. I just put all the S's. I thought it might have been an S or D.
Sorry, no, that is DS. So if you remember for Gauss's law, you had to wrap an entire three-dimensional surface around your charges, and from there you calculate the flux, and from that you set it equal to the amount of enclosed charge. There's a proportionality constant in there too, right? Notice the proportionality constant is on the other side here. You guys see that? So if we were to compare this with Gauss's law, very similar structure, right? Gauss, you have to have a surface. For Ampere, you have a loop. This is a line integral. It is not an area integral, so it's not a flux. And all it says to do is wrap a loop around a current. And in wrapping a loop around your current, you are enclosing a current that passes through your loop. Now, what you need to do is integrate the magnetic field along the entire loop. You're going to add up all of the contributions of the magnetic field that are acting on that loop. So to appreciate that, I'm going to draw this a little different. Current coming out of the board towards you with the loop I'm choosing to use is a loop that is concentric with the line of current. That means that every piece of the loop is the same distance away from the wire. So I'm going to use, to be consistent with what I have written over there, I'm going to use Z, because my point is located a distance Z away from the wire. Using the right-hand rule, I can articulate that there is a magnetic field that is this way all around the loop in every place tangent to my Amperian loop. Amperian loop, right? Gaussian surface, Amperian loop. Are we seeing the symmetry here? So if I want to use this to figure out the magnetic field, which is what we're going to do for this example, I drew a loop that would have a constant magnetic field everywhere along my loop so that I could add up all the contributions of the magnetic field that exist inside the loop. So that's what we're going to do. It's a line integral. there's two things you have to do with your line integrals. You have to give the segments of arc in your loop direction, but that's an arbitrary choice. I'm going to choose my direction for my integral to be as shown counterclockwise. So each piece of loop, I'm going to say the ds is in that direction. And this dot product will be the angle between the magnetic field and the vector direction of my loop. You'll notice I'm choosing them to be in the same direction, so that this will automatically be a cosine of 0. And I'm choosing my loop to be concentric with the current so that I am the same distance away from the current all the time. We know that magnetic field varies with distance, so if I'm the same distance away all the time, I would expect that my magnetic field will be the same value everywhere around the loop. Does all that make sense? Yes, sir.
Is there ever a time then where we wouldn't have it to be the cosine of 0?
Yes. Yeah, we'll see some examples of that. But believe it or not, not very often. Far less often than we did with Gauss's law. We can only use Amperes law in very, very narrow circumstances. Although it is a law and is always true, just like Gauss's law, using it in practice for anything that's not symmetrical, nearly impossible. Same will be said, same was true with Gauss's law, right? If you had 3-point charges, you couldn't use Gauss's law to figure out the electric field. The field was too asymmetric. So we can use it here in certain circumstances because we have a very symmetrical system. Now, this integral isn't a whole lot once we find the magnetic field to be a constant and the angle to be the same each time. I will write a separate step, but believe it or not, I want to end this really fast. That's now true. I've taken care of the dot product. And in one more step, I will say, now the integral here says to add up each piece of length so that I go in a complete closed loop. So this part shouldn't be too hard to recognize that this sum is the circumference of the loop. Does that make sense? We've chosen it specifically to do that. The left side is the current enclosed, which is just I. So this is how I know what the answer must be. This has to be the magnetic field. Whether from Gauss's law, whether from Amperes law or Biot-Savart's law, that has to be the answer. Which is how I know I kept screwing up yesterday. But ultimately, this is how much Amperes law would do. Now, I said it'd be like super easy, and I made a long, you understand, this is really just me making sure I talk out what each part of Amperes law is. That once you've seen this once, this is pretty easy to replicate. We will only use Amperes law under I think 3 circumstances. This is circumstance number 1. This is how you can usually figure out pretty quickly what the magnetic field around a long current wire is. We could not use this to find the magnetic field at the center of a loop of current to asymmetrical. So only in symmetrical circumstances can we use it. But also, screwed up yesterday because I didn't get this. Kept getting other things. So let's talk about Biot-Savart now that we've seen this and now know what the answer has to be. This has to be the answer. So I want to do this. Just put you over there in the corner. So I have something to look at. Biot-Savart should give us the same answer. But to use Biot-Savart, God, it's so ungangly. It's so just nasty and no fun. Yeah. Now, from this, we developed one version of this that I can't take the integral of. I know some of you can, but I don't have it. I would have to look it up to take the integral from it. And that was the first derivation we did in terms of x. And not to regurgitate all of that, but it wasn't hard to put that together. We said that r is equal to the root of x squared plus z squared. We know we have a sign that we're going to have to use. The sign of theta is going to be z over r. And in doing those substitutions, we got, I believe, z over x squared plus z squared to the 3/2 power dx. Right, this is where we ended up. Before I said we could always look at it from the standpoint of the angle, which is where all hell broke loose. Or at least where I became less successful. Now, we also said that the best way to do this integral was to go from 0 to infinity in one direction and multiply by 2. Now, you understand how my brain probably works at this point. I know that this is the magnetic field for a current carrying wire. Except we're missing one thing, Z, which tells me that all of this must produce 1 over Z as the answer. Now, I'm sure calculus does that. I didn't. I said, there's got to be an easier way than doing that integral. And I said, let's go ahead and try and convert it to the angle, which should have worked. But I keep getting it wrong. Now, you guys are smarter than I am. I know that. I'm a feeble mind. And I was a little frustrated when you walked out of the room yesterday, not at you, but at myself, because I caught a mistake right as the bell rung. Told a couple people I left in the room there was a mistake. Went back at it. The problem is, even after I caught that mistake, it wasn't sufficient. So there must have been an entire gaggle of mistakes, perhaps. Or a few or a couple. I'm not really sure. It still could be a bunch. Michael, do you know what we're talking about? Were you in the room for that? I don't think you made it back into Jiffy, so you might not know a bunch. But what's a bunch? And a few? So, you idiots have had this conversation before. Oh, you were here. Okay. Wow, I was about to say, if this really preoccupies you guys so much that you've all had this conversation, it might be that I'm becoming more and more irrelevant. It's like a group of giraffes is a tower. You ever go down that pathway?
Tower.
Yeah, I would. The next conversation we should have should be like that. A bunch of geese, a group of puppies is a puddle. So there's lots of those. You should see, and a group of let's see, a group of, what are they? Crows is a murder. Yeah, there's another one for ravens. So
Ravens like Palmer.
so yay! I liken that conversation. Don't touch your phones. I liken that conversation to figuring out that a bunch is 4. I figure it's the same kind of conversation, right? A bunch of people have way too much time on their hands. So here's the going back to this, because I think sometimes you need to have a bit of a brain break, which I don't know if you guys know this or ever pay attention, but you guys think I just go on a diatribe. No, I needed a break. I think you guys need a break. You get thinking so hard sometimes that sometimes you just need to okay, let's stop for a second, shake it off, like the way you work a muscle, and then come back into it. The brain is very similar in that you can only concentrate for so long before you have to have a break. I feel very strongly about that you need some time to just shake it off a bit and then come back. It often helps. It did not yesterday, which is frustrating me even more. So I believe that we could put this all in terms of the angle. And in many cases, I was right, but I wasn't right all the way. And the first way I wasn't right is in looking at finding a way to change dx into d theta. I screwed that up royally. And the reason I screwed that up royally is because I believed I could do this. I believed I could take the derivative of x with respect to theta and get dx equals r minus sine theta d theta. And that's wrong. R is in terms of x. So that was the first mistake I made. I made it early in my notes. And once I made that mistake, I was doomed. This isn't true. So you have alternatives on how to do this, but the best alternative is to not use cosine at all and to use tangent. So if you use tangent, tangent is z over x. So I can do this as, I can do x. It is z over x, right? Yes. So x tan theta equals z. This isn't going to work either. Well, this is the only thing I can think of to do, but this isn't going to work. And the reason just became very apparent to me why it won't. Because I'd have to do it this way. Or I guess I could use I take the derivative and just use the multiplication rule. But the right side, if I do that, the right side is going to be 0. Right? If we use the multiplication rule, can we do d theta of that? It's the derivative of the first times the second plus the derivative of the second times the first, right? So derivative of the first times the second would be dx d theta times tan theta plus the derivative of the second times the first is going to be x over cosine squared theta, right? Secant squared, but same thing, right? Equals 0. So I'm not sure this helps us in that we want to replace dx, but it's going to put an x into our equation. But we can do it, and this is where we'd have to go. So I believe this is correct as the derivative goes. d theta of that should produce this. What do you guys think? You guys are more close to calculus than I. So I have two people who are better calculus students. Let's hear from Michael first.
I feel like what you're trying to do anyways is a trig sum. So why don't you just do a trig sum?
It's going to be a trig sub. Yes, you're right. Because I thought it would be easier. It doesn't look like it's going to be. See, when I made my mistake, it was a hell of a lot easier, but it gave us the wrong answer. So it was useless. And I was under the hopeful idea that this would make it easier. I just don't think it's going to. Yeah?
I'm sorry. My thing is just I want to try and understand your line of logic from your first line for tan theta down to the second line to the third. So I get that you distribute. No, can you re-explain the?
I multiplied both sides by x.
Right. Okay.
I am taking the derivative of both sides with respect to theta.
Okay. Thank you.
Okay. And you're probably right. I think what we are going to end up with is the trig identity that will be subbed in for what we have to do here. That's what I think we're going to get. But I was unsuccessful twice yesterday.
It's also confusing because the thing that I did was I thought x equals z tan theta, but when you started, all your work is correct, but now you have z equals x tan theta. It's the opposite. Something you made over. That's what kind of confused me at first. All your work was correct.
Well, I don't know. I am lacking in confidence right now, which is why I thought we talked this out together. So my feeling is I could press on here. I need to get the x's on one side and the thetas on one side and put those together so I can do my sub. But I also know I could, right now, replace the x here with, z over tan theta, right? Shouldn't that work? And if I do that, I should be able to, I don't know. That's all I can think of to do right now. Yeah. I don't want to do it that way. Because maybe, but I don't think so. So here's what I propose. I'm going to run out of space, but I'm going to write dx d theta tan theta equals minus x over cosine squared theta. And I need to get the theta parts and d theta on one side, so I'll divide both sides by tan theta. So dx over d theta equals minus x over tan theta cosine squared theta. Divide both sides by x. So dx over x equals minus d theta over tan theta cosine squared theta. Now, I guess what I could do is leave the x over on the other side because I have to sub in for dx. Correct? Now, x is z over tan theta. Right? So tan squared theta. And isn't tan squared theta times cosine squared theta sine squared? So, sub? I believe everything I've done is correct.
Yeah, I get this in there. So if you're letting x basically equal z cotangent theta, and basically what this is doing is the denominator is going to simplify because cotangent squared plus 1 is cosecant squared, and you're multiplying by cosecant squared because of that dx equals negative theta, so it will eventually cancel.
And this should be the trig identity. That's what I was hoping. Because sometimes this trig identity for me was always a tough one to swallow when I was taking calc. But this is where it comes from. But we're gonna have to need some space here. There. All right, so I see mu naught I over 4 pi. And we have still three pieces. We have the dx and the sine theta. Oh, and the r squared. So we're going to sub in all of these things. So let's start. We moved it, but r is z over sine squared. Right? Do you guys see that? So r is z over sine squared theta. I have r squared right there. So the first sub.
Isn't that just sine?
Yeah, I'm sorry. I'm thinking ahead where I have to square it. So I have r squared here. So that's going to be sine squared over z squared. I'm just replacing the r. Dx minus d theta over sine squared theta times z. This seems too easy. Do you see all the sine squareds canceling out? I mean, I do. But I'm hoping I didn't make a mistake in any of my substitution. Yes, sir. Point it out now before we go any further.
That's probably the next step.
Let's just stop right here before I go any further, because I'm getting myself all wrapped up in this. Is there any substitution I've made incorrectly? Y'all got focus faces. That's good. Lucas? Well, I didn't yesterday either, but you know, we're about to just get a single sine theta, which seems way too easy. But way too easy. But I'm still making sure, because I'm going to cancel all that crap out, and we're going to get the parts that don't change. So all that. That gets rid of the z's and all that other stuff. I have a negative sign, which is explicit here, or implicit. And then I have sine theta d theta. And then we're going to integrate this from 0 to pi over 2 times 2. Now that integral, to me, is a lot easier than this integral, except it took, like, you know, pulling some teeth to get here. Mostly back molars, which were painful and had like 4 roots wrapped around nerve endings and stuff. But the actual calculus part, nice, you know, just minus cosine, kind of like that sucker. So, and of course, that's also going to give you a cosine, or I'm sorry, an integral that just shows up to be 1, right? It's going to be, the negatives are going to cancel, and I'm going to get 1. And that gives us the answer, but it was tough.